Hello students, welcome back to the tetrahedron chemistry classes. So guys, today I am going to solve a problem which is based on the combined spectroscopy. Okay, actually this question has been posted in my chemistry group, and generally I don't get that much of time to solve the problems which are generally posted in my group. But today I am not in my office, I am in my home as my elder son is not keeping well, so I am taking care of him. So in between I have spared the 5 to 10 minutes time to solve this particular problem. So let's see what is the problem actually. Let's focus on my computer screen, guys. So you can see here what is written here. An organic compound X gave the following spectral data, and in which you have been given the mass spectral data, where you have been given the four fragments, fragments corresponding to the 73, 91, 149, and 164 M by Z unit, right? And then you have been given an IR data which is corresponding to the 1730 centimeter inverse. It is generally a carbonyl compound. It's quite clear if you are getting the band somewhere around at 1730, most probably it is your carbonyl group. But it depends on the type of the molecule, whether it is this carbonyl group belongs to the aldehydes, it belongs to the ketones, or any other functional group. Let's see what is this actually, right? And then you have been given the proton NMR data. First of all, you can see here what is given here. Uh, Delta 2.0 ppm. You are having a singlet which is corresponding to the three protons. So three protons are nothing but it is the CH3, right? And all three hydrogens are actually the similar kind, are of similar kind. So you are getting the singlet, right? So basically this is the CH3 which is resonating somewhere around at 2.0 ppm. And you know your alkyl protons, your these alkyl protons generally they resonate between 1 to 2 ppm, right? But it is at 2 ppm. That means it is somewhere near to the some electronegative element. Let's see. Let we will see uh, uh, what could be the possibility, right? And then you can see the next signal is where 2.93 ppm, two proton triplet. Two protons means you are having the CH2 group, right? And if it is a triplet, that means it is connected with the another CH2, right? If you apply the n plus 1 rule to get the multiplicity for these two protons, then you know in the vicinity you are having the two protons. And if you apply the simple n plus 1 rule, that means 2 plus 1, that will give you the 3. That means this will give you the triplet. These two protons will give you the triplet. This is called the two proton triplet. And similarly, same is true for this one also, right? If you are calculating the splitting pattern for this one, so in the neighbor you can see the two protons are here. So again you will apply the n plus 1 rule, that means 2 plus 1, it will give you the 3. So triplet. So this will give you the triplet, this will also give you the triplet, right? So you can see here triplet at 2.93 and triplet at 4.90. Suppose this triplet is somewhere around at 4.90 ppm. That means it is near to the electronegative group, most electronegative group. Okay, most electronegative group. And this one is actually resonating somewhere around at 2.93. Okay, so this is not this may be near to the electronegative group or some other pi system. It may be near to the some other pi system. We will see what could be the possibilities for this also, right? And finally you are having the very important data. You are having the peak at 7.3 ppm, and this correspond to the 5 protons, and you are getting the singlet. However, in actual practice this is not a singlet, but in the simple problems, the problems of the kind which is given on your screen also, you can regard this as a singlet, right? So now what we can do, we can put the pieces together. How we can put the pieces together for this one? Say you are getting the singlet at 7.3 and corresponding to the 5 proton, that means benzene ring is probable. All these five hydrogens are here. 1, 2, 3, 4, 5. Okay, and then you are having the CH2 group, and then again you are having the CH2 group. Got it? Just like that only. Okay, and then what you can do, you can connect it with oxygen, and then you can connect it with the carbonyl group, and then you can not like that actually, right? So uh, let's remove it. What I can do, I am not removing, I am simply writing just like that. This is CO and this is CH3 because I am not having that oxygen data here. So this is the possibility of the structure which I am getting from the proton NMR spectrum. But if you count the total weight of this particular compound, right, you can count the number of the carbons. This is 1, this is 2, this is 3, 4, 5, 6, 7, 8, 9, 10. 10 carbons are there. That means 12 into 10. 12 is the atomic weight of the carbon. So you will write the 120 here, right? 12 carbons, right? And then you are having one oxygen here. So for one oxygen, your oxygen is 16. So 16 into 1, that will give you the 16 again. Then you can count your hydrogens. 3 to 5 to 7, 7, 8, 9, 10, 11, 12. So 12 of hydrogens are there. So 1 into 12 you can write here. So this will give you the 12. If you add all of them, then it will give you 148. Okay. So this molecule is corresponding to the molecular weight of 148. But you can see here in the mass spectrum data, you are having the fragment at 164, which is not corresponding to this 148. So what is the trick? How to approach such kind of the problem? So 164 is given, quite fine. What you can do, you can subtract 148 from it. Then you will get 6 and 160, right? That means 16 unit extra you need to get the 164. And what this 16 correspond to the mass spectrometry, it is your 16, right? It is your oxygen actually. So what you can do, you can write 16 and this 16 is corresponding to the oxygen. And if you add these two, then it will give you 164. Now this 164 is there. That means you need to add one of the oxygen to this particular formula. So I am adding my oxygen here. Okay. See, if I add my one of my oxygen here, then I can write the structures correctly again. It will look more clearer to you. This is this. Then your CH2. Then again your CH2. This is your oxygen. This is carbon double bond oxygen. This is your CH3. Okay. So this could be the structure. Now the important thing is that the chemical shift. You know this. These two hydrogens, they are near to the highly electronegative oxygen. That means this signal must be downfield. So it will resonate very downfield, somewhere around at 4.3 ppm. Okay. And you are getting the triplet for this one. And this triplet will correspond to the two protons. It's a two proton triplet because CH2 is there. And again, you can see this CH2 is here. So for this CH2 again, you will get a triplet. And this is just, see, if you apply the inductive effect, right? If inductive effect would be less, minus inductive effect would be very, very less onto this particular CH2. So it will go the downfield, but it will not go that far compared to this CH2. So it will again resonate downfield, two proton triplet it is again, but this will resonate somewhere around at 2.90 or more correctly 2.93 ppm, right? And this CH3, which is near to the electronegative group, carbonyl group. This carbonyl is electron withdrawing, but not that much electron withdrawing. So this will shift this the signal slightly downfield, and it will resonate somewhere around at 2.0 ppm, right? And then you are having this carbonyl group, right? And this carbonyl group is basically present, and it is reflecting in the IR spectrum also at 1730 centimeter inverse, right? So this is the characteristic of the ester also. Okay. So, and then finally, if you want, then you can see after 164. See, this is your 164, and then you are getting the 149. So how to solve this one? 164 is given. If you subtract 149 from here, then this will give you 15, right? This will give you the 15, and 15 mass unit correspond to the CH3. Okay. So if this molecule undergoes the alpha cleavage and it cleaves from here, so what you can do, you can subtract minus CH3 here, that means minus 15 here. So the remaining fragment would be like that only. Benzene ring, this is CH2, this is CH2, this is O, C double bond O, right? This will give you the peak, and that will correspond to the 149 M by Z value, right? So what I can say, this structure is the correct structure. If you shift this oxygen from here to here, then this will be your wrong answer. So this is how you can solve such kind of the problems by the very correct approach to get the information from the data which is given in the question. I hope you understood the problem, right? And so that's it for today. Thank you very much.